Okay, welcome ladies and gentlemen to this video lecture. So we're busy discussing this example. We want to show with f defined as follows. F takes on the value 2 when x is less than 1 and takes on the value 1 when x is greater than, oops, that should be a 1 actually, greater than 1. And we want to show using the definition of continuity that f is not continuous here at 1. And we discussed what we actually have to prove. So we wrote out the definition of continuity, expanded the definition of expanded the definition of the limit in the definition of continuity, and we negated that statement, and we pointed out that there is what is called a hidden quantifier in the definition of a limit. And then we wrote the following proof outline. Okay, so what we will do now is we will first give an intuitive idea of what is going on, and then we will complete this proof outline. So let us just think of what is going on here. So our function looks like this. It has this discontinuity there. So it says there, here, we must find an epsilon so that for any delta there exists an x which is within a delta distance of 1, but for which the function value at that x is further than an epsilon distance from 2. So 2 is over here. So the idea here is we must find some epsilon so that if we look at the strip around 2, around the value 2, we must now be able to, for every delta, doesn't matter what it is, so for any delta, if we look at this interval centered at 1 with radius delta, we should be able to find an x somewhere in this interval. So if x satisfies that inequality, it means it lies somewhere in this interval, but for which the function value is further than an epsilon distance from 2. So if this is epsilon, then you immediately see where you should choose your x, because if you choose your x over here, if this epsilon is like so, then the distance of the function value here, which is equal to 1, is further than 2 over there. So this distance is bigger than the epsilon distance there. So what is the idea? Why don't we take epsilon to be half of the distance from 1 to 2? So half of this distance. So what is half of that distance? That distance is 1, so why don't we take epsilon to be a half and see what happens. So we define epsilon to be a half. And now for any delta, so let me erase what's going on here and start again. So we have now defined epsilon to be a half. And now fix any delta. So it doesn't matter what it is. It can be like so. So if that distance is delta, it doesn't matter what it is. And so now we are looking for an x so that the function value, or the point on the graph of the function, does not lie anywhere inside of this strip of width or of radius 1/2. Why 1/2? Because we chose our epsilon to be 1/2. And why did we choose 1/2? We chose 1/2 explicitly because if we choose this radius to be 1/2, you see that if you draw this strip around the value of 2, there will always be, doesn't matter what you take your delta as, all the points here, if we look at their function values, they are further away from 2 than the radius of this little strip around 2. So we can take any, for our x, we can take any point here. So that is 1. Why don't we just take this point exactly halfway between 1 and delta? So why don't we define x to be, so what is the average of 1 and delta? So that is 1 plus 2 over 1 plus delta over 2. So let's just take x to be 1 plus delta over 2, and this is this point. This is the average of, oh actually no, not 1 plus delta, the average of 1 and 1 plus delta. So this point here is 1 plus delta, and we want to take exactly the point in the middle here. And let's see, what should that be? What is that point in the middle? That is the average 1 plus delta over 2. So that is 1 plus delta over 2. So we define our x to be 1 plus delta over 2. And now we see here we use this delta. What are we allowed to use to define x? We're allowed to use any of our previously defined symbols, but we're only using our delta. Good. And now let us verify that this actually holds. So let's do that. So 0, well, let's write it this way, x minus 1 in absolute value is equal to, and now let's just substitute x in there, 1 plus delta over 2 minus 1, and oh, I miswrote that is 1 plus delta over 2. This is 1 plus delta over 2. The 1's cancel, and we're left with this absolute value of delta over 2. But delta is positive because it was chosen to be any positive number. So this is just equal to delta over 2, which is less than delta. And delta over 2 is definitely positive. So yes, this statement is actually true. So now here we see we have verified that. And now we also need to verify that this holds true. So let's do that. Let me move this sketch down a little bit. So now what are we going to do? Let's take a look at f of x minus 2 in absolute value. So what is, actually let's write it over here. F of x minus 2 in absolute value. Let's substitute in the value for x, f of, and what is it, 1 plus delta over 2, 1 plus delta over 2 minus 2. But this is equal to, so if the input of f is bigger than 1 over here, then the function value is equal to 1. So this, here we have 1 plus something positive, so this thing is bigger than 1. So this is equal to 1 minus 2, which is equal to minus absolute value of minus 1, which is equal to 1. Okay. However, how did we choose our epsilon? Our epsilon is equal to 1/2. So 1, maybe let's move it just a tad to the left. But 1 is bigger or equal to 1/2. And now magically we're done. So this here we see here we're taking our x to be over there, the average between 1 and 1 plus delta, explicitly as that, and looking at the function value, and we're looking at this distance, the distance from the value 1 to 2, and we see that this distance is equal to 1, which is bigger or equal to the epsilon that we took. Okay, and that completes this proof. I will see you in the next one.